everybody. In this video, we're going to look at how we can analyze one of the CART systems with a momentum chart, and then we're going to look at the forces that are involved for an object in uniform circular motion, just like the tennis ball on a string that we saw earlier in DL. For this video, we're going to be analyzing the scenario where we have two carts of identical mass traveling at each other and then bouncing off. One of the first things we should identify when thinking about these systems is whether or not the collision is elastic or inelastic. In collisions like these, momentum is always conserved, but kinetic energy is not always conserved. Remember that kinetic energy does not depend on the direction that an object is traveling. It only depends on the speed that it is traveling. So, for example, if we have two carts of the same mass that are traveling at each other at the same speed, the total momentum of the system is zero, while the kinetic energy is non-zero. If the two objects then collide and stick together, they're going to stop moving entirely. The final momentum will obviously be zero. Momentum is conserved. And the final kinetic energy will also be zero. Kinetic energy will not be conserved because we started with some kinetic energy. In general, we can assume that collisions are either elastic or inelastic. In the context of these carts, we're generally going to assume that collisions that involve two objects bouncing off each other are elastic. So for the purposes of this example, we're going to assume that this is a perfectly elastic collision. Of course, in reality, nothing is perfectly elastic, but for our purposes, it's just fine. Let's start by looking at the initial values of the momentum. We know that these objects have the same mass, and they're traveling in opposite directions at the same speed. So we know that the initial momentums of these objects are equal and opposite. Cart 1 is moving to the right, while cart 2 is moving to the left. Because these two momentums are equal and opposite, we know that the total momentum of the system must be zero. We're also going to assume that there are no external forces on these two carts. The only forces that are in play are forces that are between the carts themselves, and therefore internal to the system. This means that the change in momentum for the system overall must be equal to zero, and therefore the final momentum of the system overall must be equal to zero. Now let's talk about what the final momentum of the individual carts should be. To figure this out for sure, it's important that we remember that this collision is elastic. After the collision, the carts will still be traveling in opposite direction, and the total momentum of the system will still be zero. Because the carts are the same mass, we know that this means the carts must also have the same speed after the collision. If one cart was traveling at a different speed after the collision than the other cart, then there would be no way for the momentums to cancel out perfectly. But how fast are they traveling after the collision? Is the speed of the carts going to be the same after the collision as it was before, or different? Well, to get that piece of information, we need to think about the other constraint we placed on our system. We said that the collision is elastic, meaning kinetic energy is conserved. So we have to think about what speed the carts must be traveling afterwards, such that the kinetic energy is the same as it was before the collision. In order for the kinetic energies to be the same, the speeds must be the same as they were before the collision. If the speeds were greater, we'd have more kinetic energy than we started with, and if the speeds were less, we'd have less kinetic energy than we started with. We know that this kinetic energy is divided up equally between the carts because they have the same mass and the same momentum, and therefore have the same speed. So what is our final state for these objects? The final momentums of the objects are just the opposite of their initial momentums. They're traveling at the same speed as they were before the collision, but in the opposite direction. So what does the change in momentum look like for the individual objects? Well, we know the change in momentum for cart 1 has to point this way. because its final momentum is in this direction and its initial momentum is in that direction. So its change must also be in that direction. But how large is that change? Well, let's just think about vectors. If we drew a vector that was this long, the final momentum of the cart would be approximately 0, because this vector and this vector are approximately equal and opposite. But we know that the final momentum is not 0, it's this. So we need to add on more momentum in order to get this cart to its final momentum. What about the change in momentum for cart 2? This turns out to be extremely simple. We could use the same analysis that we used to find the change in momentum of cart 1, but we don't even have to do that. We know that the total change in momentum for the system is 0, and we know what the change in momentum for cart 1 is. In order for the change in momentum of cart 1 plus the change in momentum for cart 2 to equal 0, they must be equal and opposite. The last thing that we want to do is write down an equation for this momentum conservation. We can, in fact, write down 2 equations because we know that kinetic energy is conserved. We'll start with momentum, though. Saying that momentum is conserved is the same thing as saying the initial momentum and the final momentum are equal. So let's write down the initial momentum, the final momentum, and set them equal. We've discussed that momentum is a vector, but because this is a one-dimensional problem, in other words, since the cars can only move to the left or to the right, we don't need to be thinking about vectors in this case. What's the initial momentum of the system? Well, it's just the momentum of the first cart plus the momentum of the second cart. And what's the final momentum of the system? Well, it's just the final momentum of the first cart plus the final momentum of the second cart. I want to point out something very important that you always need to do when writing these equations out. In this problem, we have 4 different velocities. The initial velocity of cart 1, the initial velocity of cart 2, the final velocity of cart 1, and the final velocity of cart 2. We keep these velocities straight by adding the subscripts. For example, here we have v subscript 1i, meaning the initial velocity of the first cart. Here we have v sub 2f, meaning the final velocity of the second cart. I've also put subscripts on the masses. Well, in this case, the masses are the same. This may not, in general, be the case. You have to be careful to include these subscripts whenever you're doing a problem like this, because if you don't, you might mix up some of the numbers. You might plug in the velocity of cart 1 when you meant to plug in the velocity of cart 2, or vice versa. There's actually one more equation we can write down. Since energy is conserved, we can also write down an equation that says the initial energy is equal to the final energy. All we have to do is take the initial kinetic energies of the 2 carts and add them up, and set them equal to the final energy of the 2 carts added up. That equation looks like this. And there's our 2 equations for this problem. This equation tells us that conservation of momentum applies, and this equation tells us that conservation of energy applies. Next, let's take a moment to look at how forces work in the case of the tennis ball in uniform circular motion. In this drawing, we're looking at the tennis ball from the side, not from above as we did in the video. We'll see why this is important in a moment. Now, there's one thing that could cause us some headaches with this problem. While the speed of the ball is remaining constant, the direction in which it's traveling is changing all the time since it's going in a circle. This makes it really hard to write things down for the tennis ball if we're using our usual x and y directions. Let's use a different set of coordinates instead. We'll take our first coordinate to be towards the center of the circle, and our second coordinate to be straight up and down. This turns out to be totally fine to do. These two directions will always be at right angles to each other, so we're allowed to use them as our coordinate system. Let's ask ourselves what forces are involved in this problem. What's the most obvious force? Well, that may be a matter of opinion, but for me, it's the force that the string is placing on the ball. The string is always pulling on the ball to make it turn. The string is only able to provide a force along itself. So the force on the ball from the string points in this direction. What's the second force on the ball? Well, it's gravity. Although the ball is swinging and staying at roughly the same height, gravity is still acting on it just as it always does. So there's a gravitational force that points straight down. Typically, we like to draw things as a free body diagram. A free body diagram is just a diagram that only talks about forces. It doesn't tell us anything about the shape of the objects or how they're connected. The free body diagram for this case looks like this. T stands for tension. It's the force that the string is exerting on the ball. We want to know how this force and this force are related. To do this, we want to break up the tension force into its two components. One component that points directly towards the center of the circle, and one component that points up and down. Looking at this diagram, we should notice an interesting result. It's not actually possible to swing the ball in such a way that it makes a perfectly horizontal circle. No matter what we do, there will always be a force from gravity pointing straight down. We have to have some force that can counter that, otherwise the ball would just fall out of the air. The only thing that can provide that is the tension force. And so the tension force must always have a component that points vertically to cancel out the gravitational force. The other piece of the tension force is the piece that points directly towards the center of the circle that the ball is traveling in. This force has to exist because the momentum of the ball is always changing. It's not the speed of the ball that's changing, but the direction of the ball that's changing. This force that points towards the center is responsible for the constantly changing momentum of the ball. Since the change in momentum is proportional to the force, the change in momentum must always point in the same direction as the force. So the change in momentum for the ball is always towards the center of the circle. This may not match with your intuition, but it turns out that this is how it works. We won't spend the time going over the specific math of this case here. It's just important that you know what all these forces are doing. The gravitational force is pulling the ball towards the center of the Earth, because that's what it does for everything with mass. The vertical component of the tension force is counteracting this gravitational force and keeping the ball suspended in the air. Finally, the part of the tension force that points towards the center of the circle is ensuring that the ball is always changing its direction as required. Momentum and forces are super important in physics, so we're going to continue talking about them next DL.